Thank you very much for being with us today, Álvaro.
Thanks for inviting me.
It's a different setting from the original we had imagined, in a pub with a lot of people. But okay, this didn't work out, but I think we're going to have very good time tonight, have fun. And I want you to tell us a few things about yourself. Who are you? Introduce yourself to us.
So my name is Álvaro, as you said. So I was born in Spain, and now I'm working here in Germany, in Cologne, especially, so not in Bonn. So I'm at the university. I'm a scientific researcher. So I finished my PhD some time ago, and I moved to different parts in the world, and finally I ended up being here. And my research is mainly star formation. So I want to understand how the stars like the ones that we can see in the night, so how are they formed?
Fantastic. You said you went to different places around the world. Where did you move?
So I'm from a small village close to Barcelona, a small city. I should say city, it's not a village, but just to make sure that no one gets upset with me if they see this. And I stayed in Barcelona. I did my physics degree there and my PhD, but part of my PhD was also done in Mexico, in a city that is called Morelia at the center of Mexico. And after that, so I moved for a couple of years to Florence in Italy, a really nice city. It's a pity the situation that we have now with the coronavirus, but I hope everything will get back to normal soon. And then after that time there in Florence, I moved here to Cologne. So I was probably tired of the good weather and good food in Southern Europe, and I decided to move to the north of Europe just to enjoy the rain.
But they have very nice beer here.
That's true.
Right?
But I'm drinking water now, so something is wrong with me.
So. Something is wrong, okay. But it's okay. I will balance it out. I have a Kölsch here.
That's good.
So now it's okay. Fantastic. I really like how you traveled around and you settled here in the beautiful area of, outside Bonn, basically, right?
I see.
Outside Bonn. Good. So tell us, Álvaro, why did you choose astronomy in the first place?
That's an interesting question. And so I would say it's hard to answer, but probably I could go back when I was a kid. So probably all of us, we can go back to when we were kids. And I remember, so I'm from close to Barcelona, but my parents are from a village close to the city of Madrid, so in the center of Spain. And every summer and winter, we were going there for some weeks. And then I remember spending nights there, just laying in the floor, in the ground, watching the stars and bringing my grandmother outside to tell her, so this star is that, this other star is whatever, so this constellation is that, so trying to guide her. And I think when I was growing up, then I had to take a decision at some point, and I had two different options. So one was going into astronomy, the other was doing paleontology or archaeology. So these were my two big interests at that time. And I have to admit that, so to do astronomy, I had to study physics. To do archaeology, paleontology, I should go more in the direction of history or geology. And I'm a really big fan of history, of learning, reading books and so on. But somehow, I don't know why I decided to go for the more scientific, numerical aspect of my life. And I ended doing physics. And then since the beginning, I knew that I wanted to do astronomy when I started physics. And here I am.
So instead of becoming Indiana Jones, you're Indiana Jones of the universe.
Exactly.
So I
like
hope that.
Maybe something close to Han Solo, but I don't know if it's...
That's nice. Why not? In the near future. No?
Exactly.
Yes. Fantastic. I think, as you said, every one of us has a story from our child years related to why we chose astronomy. And I've talked to other people too. And even myself, at some point, I wanted to become an archaeologist. And I think it's influence from Indiana Jones.
Exactly. I think Indiana Jones and Jurassic Park was the other kind of movies that were happening when I was a kid. And I think this biased my way of thinking.
But astronomy won, and astronomy should be lucky because you are doing very amazing things, a lot of amazing things. And before we go into specifics about the things you study and tell us a bit a typical day of an astrophysicist. What do you do at your work?
So I would say, first, I probably should mention that for the people who do not know how astrophysicists work, so it's that there are mainly two types, let's say. So one is the observers, and the others are the theorists or people working with numerical simulations. So, and I think the working days of both of them are pretty similar, with the difference that observers, we have the advantage that we can move around the world and go to really interesting places just to use the telescopes that they have there. So essentially the working day that I would have, so it could be divided either if I'm observing or if I'm working from the office. So if I'm observing, I'm in a really remote place at the top of a mountain, isolated with no one. So it's like perfect. That was a perfect training for what we are doing now. So we are in isolation. So that was, ideal. So, the locations there are really amazing. So no contamination, almost no light in most of the cases. So you can enjoy the sky, the night sky, and you get to know how these big machines, these telescopes work. And this is something really, really interesting. So it's also exhausting because you have to spend many, many hours observing. So the day would be probably waking up at some time just to prepare the observing files that you need to execute in the telescope, and then spending many hours in front of the telescope just trying to record data, and then eating, sleeping, observing, eating, sleeping, observing. But it's a nice location. Then once you have this data, so I can move to my office, and this would be the most of the time, so the kind of work that I have. So it's, I would say, 90% of the time or 80% of the time. And it could be said that I'm sitting in front of a computer analyzing all the data that I have processed. And then at the same time, so I spend many hours with meetings, discussing with other people about the scientific results that we are encountering. So what to do next? So if we have found something interesting, so what does it mean? So can we try something new? So it's brainstorming new ideas, scientific ideas, trying to solve the problems that we are facing. Then at the position that I'm now, so there are several students, so I also spend time supervising students, which is also kind of scientific discussion because you can discuss with them what to do next or what they plan to do or what they are doing. So, and then also spending a couple of hours per day just answering emails. But I think this happens to every kind of work in the world. But the normal work day, it's meetings and scientific discussions, and then working in front of the computer trying to understand what the telescope was recording.
Surely you have some time to read articles and...
Sure. So, yeah, exactly. So indeed, in order to understand or to decide what to do next, so or in scientific discussions, so we need to keep updated with new discoveries. And for this, so the publication that other people are publishing every day, so are quite relevant. So this is what more or less guides all of us in the direction of, okay, so this group of people found this interesting thing. So can I find something similar that explains better the questions that they remain open? Or, okay, they found something, but it does not fit with what I know that should be happening. So can I find something that complements what they have and try to bring light to this scientific discussion that the whole world, so different groups are having with respect to one topic. So reading papers, I think it's also fundamental part of doing research. Mm-hmm. And I think it's really critical. So for people starting in the beginning, so getting to be up to date with the new discoveries, I think it's quite important.
And going to seminars in your institute and
sure.
conferences and talking to other scientists. And we are lucky as astronomers because the observing telescopes are in nice places, Hawaii, Chile, Canary Islands. Also, our conferences are held in very nice places, Hawaii, Chile. Canary Islands.
I think this is done to make sure that also the theories can go to nice places and not only the observers. So if you hold a conference in a nice place, so everyone can go there and enjoy it.
Fantastic. Very, very good. So thank you for telling us a bit about your everyday life as an astronomer. And let's go to the science part now. You work on the process of formation of high mass stars. So tell us a bit about high mass stars. What are they? Are they different from our sun? Is it important to study them?
So since I'm studying them, I should say, they are important to study. But so high mass stars are, so the sun is one of the stars that we have close by and we know really well. And there are many stars like our sun in terms of size, mass, luminosity. But there are other stars, they are less in number, but they are much bigger. So in terms of size, they can be 10 times or 100 times bigger. In terms of mass, they can be also 10 times or 100 times more massive than our sun. And in terms of luminosity, it can be up to 1 million times more luminous. So they are also, they have another different aspect with respect to the sun, is that the process in which they live their lives, it's slightly different, or the way they end their lives, let's say. The sun will at some point become what it's known as a red giant, so will become really large with an extension that will reach more or less the distance of the Earth or Mars. So it will become really big and cold, so red color. And at some point, what you will have inside is what is known a white dwarf. So essentially the nucleus of the sun will remain there. All the outer layers will disperse with that. For the most massive stars, this is different. So what you will have is that these stars at the end of their lives, they will explode as supernova, and they can end up being a neutron star or a black hole. So this is really different to what will happen to the sun. And so in the process of exploding as a supernova, so one of the interesting things is that many heavy elements will be formed. So elements like iron that are otherwise difficult to be formed, so will form in this supernova explosion. So essentially, everything that we have around us, everything that we are somehow, was probably part or formed or produced in the supernova explosion of a massive star. So massive stars are important.
That's why they're so important, because without them, we wouldn't be here. Basically,
exactly,
right? And so these chemicals like iron, they don't happen. They don't get produced inside the star before the explosion. They don't get produced by the nuclear reactions that happen during.
A fraction can be produced, but then a relevant and important fraction is produced in this supernova explosion. So having them, it's quite relevant for them. Yeah.
Fantastic. And you said that they can either be a neutron star or a black hole. And do we know when it's going to be a neutron star or a black hole? Does it depend on their mass? Or?
Exactly. So there are different ranges of masses. And so the most massive it is, so roughly speaking, the most massive it is, easier is to become a black hole. But this is not always the case, because at some point, so during the evolution of the star, so there will be lots of winds, and then part of the mass of the star will be ejected, will be exposed. And then the final mass that remains before the explosion into supernova, so may differ with respect to the original mass of the star. So then there are lots of models that can predict and say, if the star has this mass or this mass, this will be a neutron star. If it has this range of masses, this will become a black hole. So this is pretty well modeled.
Since you said models, you said you are an observational astrophysicist. Do you also use theoretical predictions to understand your data? And why is it important?
I think this is a fundamental aspect. So if I was saying in the beginning that we observers, we have a good life going to nice locations and spending a good time at the telescopes. But without these theoretical models, we could do almost nothing. Because we can collect a lot of data, we can try to understand what we have in these images that we are recording with the telescopes, but we need to have a physical model that explains us what we are seeing. And theoretical models are doing this. So they are saying, okay, what happens if we put gravity? Or what happens if we include magnetic fields? Or what happens if we put a star here? Or so you put all these physical pieces, so all these pieces that contain physical information, and they can predict what will happen. Then once they have predicted this, we can compare with what we have observed in the telescope, and we can say, okay, what they predict and what we observe matches really well. So this means that our understanding, our theory is correct. Most of the times what happens is that what the model predicts and what we observe do not match that well. And I think this is good because this triggers more questions, more scientific questions like, okay, why this is not happening? So what do we need to do? Can we observe some things to better try to see how the model can be improved? Can we give some constraints to the model to improve it? So we need to have this constant communication between theory and observations to get to know what's going on.
To understand nature and the physical mechanisms. And you mentioned telescopes. You study these objects in many different wavelengths. Why? Why is it important to study at different wavelengths and not just, for example, in the optical, what the wavelengths we see?
I would say the more information you can have, the better. But one important aspect is that not all the objects are equally bright at the different wavelengths. So, for example, the sun is really bright in the optical, so the light that we can see with our eyes. And then in principle, by just studying the sun in this wavelength regime, so in the optical regime, we could get to know many, many things. But then there are other objects that are not bright in the optical, either because they are obscure, so their emission is attenuated by something in front of them, and then we cannot detect them. And then we need to move to different wavelengths, so to different regimes of the electromagnetic spectrum. And in this case, so the kind of research that I'm doing, I'm trying to understand a star formation. So we have to go in the direction of not the optical, but going more to red wavelengths, let's say red colors, and then we go to the infrared, and then to something that is called far infrared, that it's lower frequency and higher wavelength, and then we go to something that it's a bit farther away, that it's millimeter, and then even something farther away that it's called centimeter. And this regime, millimeter, centimeter, is what we usually call radio domain, because if you go to the wavelengths of centimeter or so the mobile phone, the radio, all these items that we have at home, they work with frequencies that are in this regime, in the centimeter, in the meter, in the millimeter domain. So we need to study these ranges to get to know objects that we cannot see, observe, or study in the optical.
I think we lost you there at the end. We had a bit of a technical problem.
Okay.
So if you can just repeat your last sentence.
Yeah, so I hope my internet connection is stable enough. So sorry for the problems. So I was just saying that these last regimes, the radio, it's really relevant for the kind of study that I'm doing in star formation, because many objects that I want to study are not bright enough, do not emit radiation in the optical regime. So we need to observe them in this regime, in this millimeter, centimeter.
And now I think I'm going to ask you a bit more about stars. I will leave the most interesting question at the end, but let's talk a bit about stars more. Where do they form in a galaxy? Are they formed in specific regions, and how do they form? So
they are formed in some structures that we astronomers tend to call molecular clouds. And these molecular clouds, we can understand that they are like the clouds that we have in the sky, but much, much, much bigger. So their sizes are about 10 to 100 parsecs, that if we move it to kilometers, is something like 10 to the 15 kilometers, more or less. So it's pretty, pretty large.
10 to the 15, that's a very big number.
This is a very big number.
10 to the 6 is a million, right? To
Exactly.
The 9 is a billion, to the 12 is a trillion. So you can understand how big it is.
It's pretty, pretty large. This is in some sense why we astronomers tend to not use these units of meters or kilometers or grams, because otherwise we would have so huge numbers that it could be hard to remember them or to operate with them easily if you want to do a quick calculation. And then we move to other units, like what I mentioned before, this parsec distance.
And that's not the one they use, sorry to interrupt you, but that's not the one they use in Star Wars, the definition of parsec, right? We use it for distance, and they use it for speed. Okay,
I think they use something, I don't know if in Star Wars or in Star Trek, I think they use one unit in the wrong way. Either it's a velocity and they use it as distance, or it's distance and they use it as velocity. Yeah, so
or time, how long it takes to go there, and they say parsecs, something like that. We should refresh our memory, watch more movies now that we have, more freedom at home.
We have plenty of time of watching the movies now. So.
Sorry to interrupt you. Please tell us more about how stars are formed.
Yes, so there are these molecular clouds that essentially are these huge objects, and they are floating, let's say, or staying in the galaxy. And the galaxy is what we know as Milky Way. So in the sky, we can see this fringe of this ridge of white dots. It's where most of the stars are located. But if you look it from distance, so if we could do this, essentially the Milky Way is like a disk with something in the center. So in this disk, we have lots of these structures that I was calling molecular clouds. And inside these molecular clouds, what we have is lots of molecules. This is why they are called molecular. And molecules, so the most abundant one is the hydrogen molecule, so 2 hydrogen atoms together. But then there are many other molecules that we can also study. So at some point, this cloud, due to gravity or due to some effect that probably may introduce some kind of turbulence or instability, this cloud will start collapsing. The process is much more complicated than this, but essentially at some point, one of these parts will become really dense. And at the center of this dense structure, nuclear reactions can start, and then a star is formed. So all this process of going from the cloud to the star, it's more complicated. So you will have the cloud that it's fragmenting into small pieces. So it can form many stars at the same time, not only one star. And then these stars can interact. The way the material is being transported from the cloud to the star can depend also a lot on the motions of the gas. So you can end having something that we call disks. So the material stays around the star for a time before it gets secreted or transported to the final point that it's the star.
And this would be a simple. Yes. Sorry, where you have these molecular clouds are in the disk of the galaxy. Are they everywhere in the disk, even closer to the nucleus, or further out? How do they?
So going back to this description of the galaxy as a disk with a nucleus in the center. So the disk has several that we call spiral arms. Mm-hmm. Probably we can find many of these pictures in the internet. So most of these molecular clouds are located along these spiral arms in the galaxy. And then when you go to the center of our galaxy is a really interesting, chaotic, and probably not so well understood region, just because it's a little bit farther away than other regions in our galaxy. And because the gravity, so the effects or how gravity is working there, so it's gravity is normal, but you have many more effects that are making the motions of the material there to behave not as smoothly as in the rest of the disk. You can still have really large clouds, and indeed the most massive, the biggest clouds are really close to the center of the galaxy.
Very interesting. So, do all galaxies have gas where they form stars from?
Not nowadays. Not nowadays.
Okay.
So our galaxy has a lot of this gas. We could ask for Kevin to know how these galaxies were before, because this is part of what he is studying. But so there are other galaxies that we can see also nowadays that are called elliptical. Before I was saying that our galaxy is a star galaxy. It's a disk with a nucleus. But others are called elliptical because they are more like an ellipsoid. It's like elongated. And these stars are older, are more evolved than these galaxies, are older, more evolved than the galaxy where we are living, the Milky Way. And they do not have gas anymore. So there are no molecular clouds. So these galaxies are not forming stars. So only on galaxies like ours or others that are also a little bit irregular in shape, contain a lot of gas and then can form stars.
Okay, that's very interesting. So we live in a galaxy that is very alive and is forming stars, right? And you also said that there is a disk around the star that is being formed, this accretion disk that creates matter. And is this how planets might get formed eventually, right?
Exactly. So so when I was summarizing the process of formation of the stars, I wanted to emphasize the presence of the disk because this is one of the key objects, let's say, in the star formation process that allows planets to exist in some sense. So the disk is a structure, it's the material that has been compressed or collected towards the center, does not go directly to the star, but remains around the star in a flattened structure that it's what we call disk. And this disk, so over time, material will flow in the direction of the star, but another part of the mass that it's containing the disk will remain in this location. And so the material that I was mentioning before that are mainly molecules in this molecular cloud are not only molecules, but there are also tiny pieces of dust that we call dust grains. It's like the dust that we have at home and every weekend we have to clean, but much smaller.
Okay.
And these are, so they remain there. And then these small pieces that are a few hundred micrometers, they can start colliding one with the other. And then under good conditions, they can start sticking, becoming bigger. They will become something like a few meters size. Then at some point, they can collide with other meter-sized objects to something more like 100 meter size or so, and we will start reaching something that it's called planetesimals. So it's like the small bodies, the precursors of the planets. And finally, you will have all these species that will collide all together and can end forming what we know as a planet. So this disk is the location where planets are forming.
That is fantastic. So if I leave the dust in my house and I don't clean it, will it form a planet?
We could try it.
Okay.
Probably it will not. So here we have the gravity that will make all the dust to go to the floor, to the ground. And the other thing is that the time scale to form planets, it's usually about 1 million years. So we could wait 1 million years without cleaning the house, and let's see what happens. So maybe we have planets.
Well, this is how long it feels that we have been in this quarantine. So maybe planets will form. But I wanted to ask a couple of things about this disk. Why is it a disk? Why do we get this? You said this molecular cloud is more like a big cloud, right? Like an ellipse, like an egg kind of shape. Why do we get this disk at the end?
Essentially so the cloud is not something that remains, it's a static and then it collapses, but it's feeling the forces of the galaxy. So since the galaxies are rotating, so the disk of the galaxy is moving around, this cloud is also moving around, and then this can trigger some kind of rotation in the cloud. So the cloud is not staying static, but it will be rotating. Then when you have an object that is really large, that it's rotating, and you start compressing it, what will happen is that it will rotate faster, faster, faster. So it's like these people that are doing ice skating in the Olympic Games or so, in the Winter Olympic Games. And then if they have the arms open, so they are big, they rotate really slow. When they put the arms really close, they rotate really fast. So this is the same thing that happens when this cloud is becoming smaller. And then at some point, so once you have something rotating really fast, the material that it's going to the center will not go directly to the center, but will preferentially go, just because of this rotation, will accumulate in a disk plane. So you have the material that's rotating that cannot flow directly to the center, but it's moved around and gets trapped, let's say, in the disk. So in the plane that it's perpendicular to the rotation axis of the cloud.
Fantastic. So how can we detect this disk where planets are going to be formed? Do we detect them also with the wavelengths you observe, the frequencies you observe that?
Indeed, I would say that the best wavelengths to observe these disks are the millimeter domain, the millimeter or centimeter, because these objects, so this cloud that I was saying, I was mentioning that there are molecules and dust. So the dust is absorbing all the radiation in the optical. This is why we cannot see anything inside this cloud in the optical, and we need to go to other wavelengths. And in the millimeter domain, we can see that the radiation that the dust particles are emitting. So in this wavelength domain, we can study dust. And then what we can do is try to identify, so if we know that the disk seen edge on should be a plane, so we can search for elongated structures at the location of where stars are forming. And then if we see this kind of elongated features, we can say, okay, this can be a disk. Other way, so if we see the disk face on, so what we will tend to see is a circular disk. And there was a recent image that ALMA reported a couple of years ago of one of these disks seen almost face on with lots of features and rings. This is one of these disks where planets can be forming.
Wow, that is fascinating that we can see with ALMA this detail so far away in in another star system, basically, right? How far away is it from us? If you can remind us a bit.
So this one that was reported by ALMA is a star that it's called HL Tau, and Tau means that it belongs to the constellation Taurus, or to the molecular cloud Taurus. And this molecular cloud, it's the Taurus molecular cloud, is at a distance of about 140 parsecs. So it's at about something like 10 to the 16 kilometers away from us. So it's pretty far away, but it's one of the closest star-forming places to the Earth. So it's far, but it's close in comparison with all the other regions.
So by observing these systems, we can understand how planets were formed in our solar system, correct?
Exactly.
And we can search also maybe for planets that have life.
That would be the way to go. Probably, so all astronomers or all people doing astronomy, so if you really ask what you want to answer in reality, so if you pull the string, probably all of us, we will end saying we want to understand life. And then to understand life, so we know that life exists in our planet, and our planet seems to be something peculiar compared to the other planets in our solar system. So we want to know why our planet has life, but not the remaining 7 or 8 planets if we include Pluto.
Thank you that you included Pluto. I also like him as a planet.
I'm okay with having him outside, but since I was a kid, I was learning that Pluto was a planet, so I keep him in mind.
Are the systems, the other systems we're finding different? And how many planets we believe can be hosting life?
So for the moment, so these numbers are changing every day, but I think a few weeks ago or a few months ago, probably we were around 4,000 planets discovered outside our solar system. So our solar system has 9 planets, so we know 4,000 more. And these planets are distributed in about 3,000 stellar systems or planetary systems. So this means that some systems, some stars, are already harboring more than one planet. And this means that the existence of stars with many planets, similar to what we know as the solar system, may be really common, pretty common. The problem is that we don't have still the telescopes or the techniques to detect them. So we can detect planetary systems that are slightly different to the ones where we are living. So in our solar system, we have the sun, we have tiny planets, the Earth is one of them, and then we have giant planets. So we have Jupiter, Saturn, Uranus, and Neptune. And we have some kind of clear distinction between small planets and giant planets. So most of these other planetary systems that we are finding, they have these giant planets really close to the star. So much closer than the Earth. And then this is telling us that, okay, these systems are really strange. Does it mean that our solar system is unique? No. This means that we are only able to detect planetary systems with these conditions, with big planets close to the star. Hopefully in the future with new telescopes, we will be able to start detecting more systems similar to the one where we are living. Nowadays, I think there are 1 or 2 that are pretty similar, so that they have also about 4 or 5 planets, and they are more or less located at similar distances like the Earth, Neptune, Mars, Venus, and so on.
That's very interesting what you're saying, because I don't think many people know this, that we cannot detect solar systems like our system because we don't have the telescopes yet. Mm-hmm. It doesn't mean that they don't exist out there. So maybe in the future we manage to find a solar system like ours, and who knows, maybe life. But
exactly. Maybe we can send a tweet there or broadcast this live show to that other planet.
Yes, we are your friends. Don't come to Earth. It has coronavirus.
Exactly.
Okay. But something stuck in my head when you said that the center of our galaxy is a very peculiar place. So I read somewhere that the center of our galaxy smells like raspberry and tastes like rum. And since we're doing astronomy on Tap Bonn,
we should go there, right?
We should host the next one there.
Okay.
So tell us a bit about the center of our galaxy, Sagittarius A star, B2, and the neighborhood that it's so has so much gravity around it and so vibrant and interactive.
So this study that you were mentioning, the title is really nice, and it's a good way to reach the public that this is what we should do. So when we do science, we should make sure that what we learn, what we discover, reaches everyone outside, and not only the people that are working on this. And this study was done by Arnaud Beloche, that it's indeed a researcher in the Max Planck in Bonn, so pretty close to where you guys are or where you are working. And this was done a few years ago. And the reason is that part of the research that we are doing when studying star formation is trying to search for molecules, a specific molecule. So when I was describing the molecular cloud, I was saying that most of the molecules that are there are this H2, molecular hydrogen. So 2 hydrogen atoms, one next to the other. But this is not the only molecule. We have many more molecules. And some of them can become pretty complex. And in the end, they can end forming what we know as amino acids, so the basis of life. So, and this is what we are trying to do. So we are trying to search for these complex molecules, these big molecules that are the precursors of this life. And Arnaud, in this study, so he was studying this region called Sagittarius B2. I will explain later a little bit why this is so important in this region. And what we found is many lines. Lines are features that indicate if a molecule is there or not. So it's like this QR code or this barcode that you have in all the items in the supermarket. But we can have this, and depending on these bars, so we can say okay, we have found 3 of them at these different positions. This belongs to this molecule, or this belongs to this other molecule. And for the first time, he found a molecule that it's called ethyl formate, that it's C2H5OCHO. So C is 3 carbons, hydrogens, and oxygens. And ethyl formate, it's relevant because all these ethyl alcohols are those that we have in the alcohol that we drink. So the beer that you were having there, it's mainly ethanol plus some other alcohols. And then if you take this ethyl formate, this is the flavor that raspberries has, and also the taste or the smell that rum has.
Yeah, it's the smell of raspberry. It's the smell of raspberry and the taste of rum.
Also, I have to say that this same molecule exists in the body of the ants, these insects.
Wow.
So, of course, it could be like eating raspberry or drinking rum or eating ants. So it could be all the same taste.
I don't think this title would go very far.
Exactly.
As a public release.
They pick the correct words to...
Yeah. You know, drinking rum and eating ants.
It's not so attractive yet.
No. Maybe not in Europe. Maybe in another place. But not in Europe, at least. So tell us... so it's very important study, right? We are finding chemicals and molecules that are responsible for life. And this exists in the space inside our galaxy, in the space between stars, right?
Yeah, exactly. So this region...
Sorry, Álvaro, we are losing you.
This is the most massive... Oh, okay.
We lost you. Can you please repeat?
Is it working?
Yes.
Yeah, sure. Is it working again? Yeah, okay. Yeah, I was saying that this region, Sagittarius B2, is the most massive, the largest cloud in the galaxy, the largest molecular cloud in the galaxy. And it has 2 particular subregions inside it where lots of star formation is happening. And so there is so much material there, because it's so massive, that it becomes easier to detect all these molecules. So we expect that all these molecules, like methyl formate, exist in many places in the galaxy, in all the star-forming regions, but we cannot detect them because they're abundant. So that the number of molecules of this type that exist, it's a little bit small. And then if you don't have many of them, you cannot see them. While in this region, in Sagittarius B2...
Okay, I think our connection is not so good.
And there are many...
Sorry, Álvaro, sorry to interrupt you. We lost you again for a moment. I think you were saying that it's important we have a big number of these molecules in order to detect them. But in other regions in the galaxy, it's smaller numbers because the clouds are smaller, right?
Exactly. Yeah. Exactly. So the densities and the masses are smaller, and then there are less of these molecules, and then it's a bit more difficult to detect them. So this is why the studies that, for example, are noted in this cloud, Sagittarius B2, are really important, because this triggered many other studies in other clouds to search for similar molecules.
And that's good, because we try to understand how life can be formed, right? And everything comes from stars, right?
Exactly. Exactly. So we have all the elements are formed in the stars, and then all these molecules, at some point, they will remain in this disk. Then they can get attached to these dust grains that are becoming bigger and bigger, that are planets, or in something smaller that are comets. So we expect these molecules to remain there. And then you just need to bring these molecules to the proper conditions to make them become amino acids. So precursors of life. So you just need to put them in the exact location within the disk to have life.
Can you remind us why this cloud is so big in the center of our galaxy? It's special, as you said, right?
Yeah.
Does it have to do with the gravity being so...
So essentially, in the center of our galaxy, we have an object that it's called Sagittarius A star. And it's a black hole. It's a really massive black hole. So it has 1 million times more mass than our sun. So it's pretty massive. And this influences all the neighborhood, the surroundings, with his gravity. So if you put a particle there, they will move attracted or strongly feeling the gravity that this black hole is generating. In addition to this, we have something that we call a bar. So our galaxy is not just a disk with the black hole in the center, but we have the disk, the black hole, and close to the black hole, we have something more elongated that we call bar. So the combination of this black hole plus the structure of the bar creates some gravity forces that makes all the gas to move in some specific orbits, and then all the gas can accumulate at some specific portion in this orbit, making a really huge and big cloud. And this is what has happened with Sagittarius V2. So all the gas around it is moving around, and at some point it gets really accumulated or gathered in one position. This is a really massive object, and this is Sagittarius V2.
Fantastic. Okay, I think we covered a lot of questions, and we learned a lot of things about about how stars are formed and all the nice things. Let's see if we have any questions from our live chat. Let me check here. Guys from home, if you have questions, here's your chance. Álvaro will be very happy to answer everything because he's been doing it already very, very well. It was very descriptive. I think we have a better understanding of how stars are formed and how planets are formed, and that dust can form planets in our house if we wait long enough. And we have one question from we have one question from the live chat, the live stream. Which stars make which elements?
So I'm not an expert on this topic. So if I say
tricky.
something
it's
not
tricky.
Not 100% accurate, I will point people to more expert people. But so essentially, stars like our sun are really good at producing elements like hydrogen, helium, and then at some point getting back to carbon, oxygen, nitrogen. So let's say simple elements. And then in supernova explosions is where you have a lot of energy and you can go to much heavier elements like iron. So you can go in this production of elements within stars or in the supernova, you can go up to iron. But so if you check carefully the reactions, the nuclear reactions that are happening inside any star, you can see that also in our sun, you can also produce a little bit of iron. So there, in all the stars, you can produce different fractions of all the elements, but in the supernova is where you can produce a relatively important and huge fraction of iron, or these more heavy elements, considering the low number of such stars that exist in our galaxy.
Good. I can contribute to that because I like that fact very much, that we have gold being created not by stars, by when stars collide, and we're talking about neutron stars colliding. So when you have two neutron stars colliding, and this is how we detected the gravitational waves and light. So the beginning of multi-messenger astronomy, it was when two neutron stars collided, and in the process, gold was created. So
that's really good. Yeah,
precious.
We should go to all these locations where neutron stars collide, bring our bags and fill them of gold, right?
Well, we know two already.
Okay.
So yes, the first one in 2017, and one I think it was announced this year. So pack your bags, and when we're allowed to leave our homes again,
we can go gold mining.
Yes, we can go gold mining. Are there any more questions? Well, I have a question. I was going to leave it for the end. You talked to us about evolution of stars, so you covered this. But the other one you didn't cover is, and I don't know if you're an expert on this, but maybe you can say a few things. Do stars form outside the galaxy?
Mm. So I have to say that I'm not an expert of anything, but I just know a little bit of things. But so do stars from outside the galaxies? So in our current paradigm or theory of how stars are formed and how galaxies exist, one would say no, because you need to have these clouds and they live within galaxies. However, there are things that we maybe do not know so correctly, and we know that there is material in between galaxies, so mainly atomic gas, but you can have also pockets of molecular gas. So it could be that you can end forming some kind of stars there. Another thing that may be happening is that you have some stars that form more or less connected to a galaxy, and then they were ejected, and they are found now in between galaxies or really distant from a galaxy. And then we could think, oh, is this a star that formed there, or it's coming from a different place? So this would be what I would say without being an expert on this topic, but...
Very nice, very nice. I think this opens more questions, but maybe for another time. I would like to thank you very, very much for all the discussion, the fantastic discussion and answering to our questions. We learned a lot of things about stars and the center of our galaxy and about planets and molecules and life and telescopes and how fancy an astronomer's life is with traveling to all these nice places.